Welcome to MLR I'm Noel, working as an assistant professor in physics, Department of Science and Humanities, MLR Institute of Technology, Hyderabad. In this video, let us see brief details about semiconductor material in applied physics course. In this video, let us see brief details about what are semiconductor materials and the classification of semiconductor materials, intrinsic semiconductors and extrinsic semiconductors. In extrinsic, both N-type and P-type semiconductors. Without delay, let us go to the topics. Now, when it comes to the semiconductors, semiconductor materials are whose electrical properties are in between conductors and semiconductors. Maybe many of you know about this definition. Basically, semiconductor materials are classified as, semiconductor materials defined as whose conductivity properties are in between or electrical properties are in between conductors and insulators. Based on band theory of solids, solid metals are classified into three categories, which are conductors, semiconductors, insulators. This classification is based on forbidden band gap between valency band and conduction band. Forbidden band gap between valency band and conduction band. In every material, there exists valency band, means in every solid metal, there exists valency band and conduction band. Based on the forbidden band gap, metals are classified into three types: conductors, semiconductors, and insulators. In case of conductors, this forbidden band gap is almost zero. In case of insulators, this forbidden band gap is very large. In case of insulators, we can't get conductivity. Whereas in case of semiconductors, there exists narrow forbidden band gap around 1 electron volt. Those solid metals are classified as semiconductors. So that here you can understand that the band gap is significant only for semiconductors, because in case of conductors, it is almost zero. So no need to discuss about band gap. In case of insulated, it is very large. In case of insulators, we can't get conductivity. So that this band gap is significant only for semiconductors. That's why semiconductors are having narrow forbidden band gap between valency band and conduction band, that is around 1 electron volt. In such a way, the semiconductors are classified. Now, the very important or interesting concept is by adding impurities or by increasing temperature. The conductivity of semiconductor materials increases. This is negative temperature coefficient, whereas in case of metals, it is decreases. I hope you can understand. So, because of this property, semiconductor materials are widely used in different electronic devices. That is, by adding impurities or by increasing temperature, conductivity of semiconductors increases. Now, when it comes to the semiconductor materials which are used in different electronic devices like diodes, transistors, and integrated chips and so on, almost 95% of electrical devices are made of semiconductor metals because of their variety of properties. Now, when it comes to our periodic table, almost 11 elements are going to behave like a semiconductors. In that, the most familiar examples are silicon and germanium. Not only silicon and germanium, some alloys will also behave like a semiconductors like gallium arsenide, phosphorus. Some alloys are also behaves like semiconductors. I hope it's clear. Now, when it comes to the classification of semiconductors, basically semiconductor metals are classified into two types: intrinsic semiconductors and extrinsic semiconductors. Intrinsic semiconductors are nothing but in which semiconductors there exists electrical conductivity due to both electrons and holes. That semiconductors are called intrinsic semiconductor. Means in case of pure semiconductors only, there exists electrical conductivity due to both electrons and holes. That's why intrinsic semiconductors are nothing but pure semiconductors. When it's come to extrinsic semiconductors, in case of extrinsic semiconductors, the conductivity either due to electrons or holes. In case of impure semiconductors only, charge carries varies. That's why extrinsic semiconductors are nothing but impure semiconductors. Again, extrinsic semiconductors are classified into two types: P-type semiconductors, N-type semiconductor. Based on impurity materials, this classification is done. Now, let us see what are intrinsic semiconductors. Now, when it comes to the intrinsic semiconductors, as I told you, the materials in which electrons and holes are produced by thermal activation are called intrinsic semiconductor. That is nothing but, in case of intrinsic semiconductors, both electrons and holes are involved in electrical conduction. For example, here I consider pure silicon material. Here you can see two-dimensional representation of silicon structure. When we consider pure silicon material, each silicon valency is 4, that is silicon belongs to 4th group elements. Each silicon is having 4 valence electrons, so that in order to get stability, each silicon atom, for example here you can see central silicon atom, each silicon atom is going to make 4 covalent bonds with the nearest silicon atoms, 4 covalent bonds with the nearest silicon atoms, in such a way that silicon atom is going to get stability, That's why here you can see it is a two-dimensional representation of silicon. So after forming 4 covalent bonds, silicon atom is going to get stability, and there wasn't any free electron, because all valence electrons, here you can see covalent bond is nothing but sharing of unpaired electrons. Here you can see, so that 4 valence electrons involved in 4 covalent bonds, so that in such a way silicon atom is going to get stability. That's why in silicon material at 0 Kelvin temperature, there wasn't any unbonded electrons or free electrons. So that at T equal to 0 Kelvin temperature, silicon material, pure silicon material behaves as insulator. Again I repeat, at T equal to 0 Kelvin temperature, pure silicon material behaves as insulator. Now, when we increase temperature, let us see. Now, with increasing temperature, here I am increasing temperature, with increasing temperature, due to the breaking of covalent bonds, in any solid material, when we increase temperature, there exists lattice vibrations. That is, atoms are going to vibrate. Due to lattice vibrations, covalent bond is going to broken, or covalent bond will be break, or covalent bond is going to be broken. Due to the breaking of covalent bonds, whatever that electrons involved in that covalent bonding, those electrons are going to behave like a free electrons. Whenever that electron behaves like a free electron, immediately that electron will excite from valency band to conduction band by using that thermal energy. Whenever that electron is excited from valency band to conduction band, there exists electrical conductivity. That's why in case of intrinsic semiconductors, with increase in temperature, electrons will excite from valency band to conduction band. Due to the whenever that electrons are excited, there exists electrical conductivity. So that with increasing temperature, the conductivity of intrinsic semiconductors increases. But at exact T equal to 0 Kelvin temperature, intrinsic semiconductor material behaves as insulators. I hope it's clear. Now, let us see the energy level diagram. Energy level diagram of intrinsic semiconductors. Here you can see valency band, and this is valency band, and this is conduction band. I hope here you can see EV. EV is nothing but higher energy level of valency band. Band is nothing but close collection of energy levels. EV is higher energy level of valency band. EC is lower energy level of conduction band. Now, EZ is nothing but forbidden band gap. Now, an intrinsic semiconductor behaves like insulator at T equal to 0 Kelvin temperature. As I told you, at T equal to 0 Kelvin temperature, all electrons are involved in covalent bonding, so that there wasn't any free electrons, so that there is no excitation of electrons from valency band to conduction band. But now, when we increase temperature, right side figure you can see, at T greater than 0 Kelvin, when we increase temperature, what happens? Due to the breaking of covalent bonds, free electrons are going to be generated. Those electrons will excite from valency band to conduction band. Whenever that electrons are excited from valency band to conduction band, there exists electrical conductivity. So that with increase in temperature, conductivity of semiconductor materials increases. So that keep on, when we are increasing temperature, due to the breaking of covalent bonds, more electrons are going to excite. So that whenever electrons are increasing, electrons are going to excite, electrical conductivity also increases. So that with increasing temperature, conductivity of intrinsic semiconductors increases. Here, one of the important thing is, at any temperature, intrinsic semiconductors are having equal number of electrons and holes. Here, you have to consider equal number of electrons and holes means free electrons in conduction band and free holes in valency band. So, though there exists some electrons in valency band, those all electrons are involved in covalent bonding, so that which doesn't involve in electrical conduction. In case of intrinsic semiconductor, at any temperature, how many electrons are going to excite from valency band to conduction band? Same number of holes are going to create in valency band, so that there exists number of free electrons. How many number of free electrons are going to exist in conduction band? Same number of holes are going to exist in valency band. That's why in case of intrinsic semiconductors, equal number of free electrons and free holes are going to exist. I hope it's clear. Now, let us see extrinsic semiconductors. Extrinsic semiconductors are nothing but impure semiconductor. As I told you, in case of extrinsic semiconductors, the electrical conductivity is due to either electrons or holes. Extrinsic semiconductors are nothing but impure semiconductors. By adding some impurity atoms, extrinsic semiconductors are going to be produced. Again, extrinsic semiconductors are classified into N-type semiconductors and P-type semiconductors. Now, let us see what are N-type and what are P-type. Now, here you can see N-type semiconductors are formed by adding pentavalent impurities. When we add pentavalent impurities to the pure semiconductor material, then the formed semiconductor materials are called N-type semiconductors. Similar way, P-type semiconductors are formed by adding trivalent impurities. When we add trivalent impurities to the pure semiconductors, then the formed semiconductors are called P-type semiconductors. Now, here you can see left side image. This is for N-type semiconductors. Now, when we add pentavalent impurities to the pure semiconductor, for example, here I consider pure silicon structure. In that, I am adding pentavalent impurities. Pentavalent impurities in the sense fifth group elements: nitrogen, phosphorus, arsenic, antimony, bismuth. These all are fifth group elements. For example, here I added phosphorus to the pure semiconductor material. Whenever when we add pentavalent impurities to the pure semiconductor, those impurity atoms are going to replace instead of mother atoms. Those impurity atoms are going to replace instead of mother atoms. So that here actually in pure silicon material, here there should be silicon atom. But by adding pentavalent impurities, that atom will be replaced by phosphorus atom. In phosphorus, there will be 5 valence electrons, because the phosphorus belongs to fifth group elements. There will be 5 valence electrons. In that 5 valence electrons, 4 electrons are involved in covalent bonding. After forming 4 covalent bonds, that phosphorus atom is going to get stability. That's why that phosphorus atom try to lose that remaining electron. Whenever that phosphorus atom, after losing that electron, that atom is going to get stability. Again, after losing that electron, that atom is going to behave like positive ion. That atom is going to behave like positive ion. So that in case of N-type semiconductor, impurity atoms or pentavalent impurity atoms are going to behave like a positive ions, and which are going to donate electrons to the semiconductor. That's why pentavalent impurities are also called as donor impurities. Donor impurities. So that each impurity atom will donate one free electron. Each impurity atom will donate one free electron in N-type semiconductor. This is the formation of N-type semiconductor. Now, when it comes to the right side image, this is for P-type semiconductor. Similar way, when we add trivalent impurities to the pure semiconductors. Trivalent impurities in the sense boron, aluminum, gallium, indium, thallium, third group elements. For example, here I added boron. Boron is nothing but third group element which is having 3 valence electrons, so that those 3 valence electrons will involve in covalent bonding. In order to get stability, that atom need one more electron. So that this atom will get one electron from nearest mother atom. This atom will get one electron from nearest mother atom. That means this atom is going to shift it from here to here. Whenever that electron is shifted, this atom will involve in fourth covalent bonding and get stability. But when this electron is shifted here there exists electron vacancy. Again here also this atom needs stability. Again this atom will get one electron from some other mother atom. In such a way, each impurity atom is going to donate one free hole. One free hole. Hole is nothing but electron vacancy, which is going to be treated as which is having imaginary positive charge. So that in such a way, each impurity atom or trivalent impurity atom is going to produce one free hole, or each impurity atom is going to accept one electron. That's why these trivalent impurities are also called as donor impurities. These trivalent impurities are also called as donor impurities. This is the formation of P-type and N-type semiconductors. I hope it's clear. In such a way, the p-type and n-type semiconductors are going to form. Now, in case of p-type semiconductors, each impurity atom is going to each impurity atom is going to generate one free hole, so that majority charge carriers free holes. Later on in energy level diagram, I will show you how that holes are majority charge carriers. In case of n-type, each impurity atom is going to donate one free electron, so that majority charge carriers are electrons. Now, let us see energy level diagram. Now, when it comes to the energy level diagram of p-type and n-type semiconductors, of course, here you can see this is valency band and this is conduction band. Apart from valency band and conduction band, there exists one more energy level, that is donor energy level. The donor energy level exists within the forbidden band gap. Actually, in between valency band and conduction band, there is no any energy level, but that is in case of silicon. But when we are adding impurity atoms, that energy may exist to that impurity atom electrons. That's why here the donor energy level exists in between valency band and conduction band. But when it comes to that actual position, the donor energy level exists near to conduction band. Here you can see the donor energy level exists near to conduction band. Why? Because already that impurity atoms lose one electron. That electron is already free electron. Whenever we supply energy, what happens? Immediately that electron involved in electrical conduction. That's why those all free electrons occupied energy is donor energy level. The donor energy level exists near to conduction band. So that whenever we supply energy, immediately those electrons will excite from donor energy level to conduction band, so that those electrons will involve in electrical conduction. And now, when it comes to that p-type semiconductors, anyhow, each impurity atom is going to generate one free hole. Those holes occupied energy level is called acceptor energy level. This acceptor energy level exists near to valency band. Because whenever we supply energy, hole is going to accept electrons. Whenever we supply energy, electrons immediately will excite from valency band to acceptor energy level. It is accepting electrons. That's why that acceptor energy level exists near to valency band. This is the representation of donor level and acceptor energy level. Now, at T equal to 0 Kelvin temperature, valency band is completely filled and donor energy level is completely filled and conduction band is empty in case of n-type semiconductor. Again I repeat, in case of n-type semiconductor at T equal to 0 Kelvin temperature, valency band is completely filled and donor level is completely filled with electrons and conduction band is completely empty. So that there wasn't any conduction electrons. That's why n-type semiconductor metal behaves as insulator at T equal to 0 Kelvin temperature. Similar way, in case of p-type semiconductor also, at T equal to 0 Kelvin temperature, valency band is completely filled and acceptor energy level is filled with acceptor electrons, conduction band is empty. So that there wasn't any conduction electrons. Again, similarly, p-type semiconductor metal also behaves as insulator at T equal to 0 Kelvin temperature. Now, when we increase temperature, here you can see energy level diagram of n-type p-type semiconductors at low temperature. At low temperature means we supplied very small amount of energy. At low temperature, initially what is going on means, initially electrons are going to excite from donor energy level to conduction band, because the donor energy level is near to conduction band. That's why whenever we supply very small amount of energy, electrons are going to excite from donor energy level to conduction band at low temperature. That's why at low temperature, electrons will excite from donor level to conduction band. And again we can say at low temperature, number of electrons in conduction band equal to number of holes in donor level. At low temperature only. This is at low temperature. At low temperature, number of electrons in conduction band equal to number of holes in donor level in p-type semiconductor. Similarly, in n-type semiconductor. Similarly, in p-type semiconductor, at low temperature initially, electrons will excite from valency band to acceptor energy level. So that at low temperature, number of electrons in acceptor energy level equal to number of holes in valency band at low temperature. Now keep on when we are increasing temperature. After excitation of all electrons from donor energy level, again due to the breaking of covalent bonds, again electrons are going to excite from valency band to conduction band. Due to the breaking of covalent bonds, again electrons are going to exit from valency band to conduction band in case of n-type semiconductor. Now, here you can see energy level diagram of n-type and p-type semiconductors at high temperature. At high temperature, after all, that means the electrons which are in donor energy level are going to excite. After excitation of all electrons in donor level, now due to the breaking of covalent bonds, electrons which are in valency band will also excite from valency band to conduction band. Now, let us compare number of electrons in conduction band and number of holes in valency band. Let us compare, because whatever the holes exist in donor level, those are not free holes. Those are not free holes, which are going to be again later on, which are going to be bounded. That's why now we have to compare number of free electrons in conduction band, number of free holes in valency band. So in this comparison, here you can observe there will be more number of electrons in conduction band when compared to the number of holes in valency band. That's why in case of n-type semiconductors, majority charge carriers electrons, minority charge carriers holes. Now when it comes to the p-type semiconductors, same way, with increase in temperature, initially electrons are going to excite from valency band to acceptor energy level. After excitation of all, that means after excitation of all electrons, again due to the breaking of covalent bonds, electrons are going to excite from valency band to conduction band. Now, when we compare the number of electrons in conduction band, number of holes in valency band, here you can observe number of holes in valency band is more when compared to the number of electrons in conduction band. So that majority charge carriers holes, minority charge carriers electrons. These are the charge carriers in case of both n-type and p-type semiconductors. Now, let us see the very important concept, variation of Fermi level with temperature and doping concentration. Fermi level is a very important concept in order to study the conductivity properties of semiconductor materials. The Fermi level position is an important concept. So that in case of intrinsic semiconductors, here you can see EI is nothing but intrinsic Fermi level. Here, anyhow, here you can see in one left side diagram, on x-axis temperature, on y-axis energy. Here this is valency band. Here you can see this is valency band. EV is nothing but higher energy level of valency band, and this is conduction band. EC is nothing but lower energy level of conduction band. Now the energy difference between EC and EV, that is nothing but energy gap or forbidden band gap. Now in case of semiconductors, in case of intrinsic semiconductor, Fermi level is exactly middle between valency band and conduction band. In case of intrinsic semiconductor, almost exactly middle between valency band and conduction band. In case of intrinsic, because charge carriers are equal concentration, charge carriers are in equal concentration, means in case of intrinsic, how many number of electrons will exist in conduction band, same number of holes will exist in valency band. That's why Fermi level position is exactly middle between valency band and conduction band. Now when it comes to n-type semiconductor, here you can see EI is nothing but intrinsic Fermi level, now which is exactly middle between valency band and conduction band. Now in case of n-type, there exists donor energy level, here you can see that exists near to the conduction band. Now at exact T equal to 0 Kelvin temperature, in n-type semiconductor, Fermi level position is exactly middle between donor level and conduction band, because the Fermi level means a simple definition let me give. The highest occupied energy level, highest occupied electrons occupied energy level at T equal to 0 Kelvin temperature is called Fermi level. That's why already up to donor energy level electrons are occupied. That's why at T equal to 0 Kelvin, Fermi level in n-type semiconductor is exactly middle between donor level and conduction band. Now when we increase temperature, I hope you know that when we increase temperature, electrons are going to excite from donor level to conduction band. After that, at high temperature, electrons are going to excite from valency band to conduction band. That's why Fermi level decreases. Here, please observe, Fermi level decreases. Fermi level decreases with increase in temperature. Fermi level decreases. At certain high temperature, it gets equal to intrinsic Fermi level. Here you can see both variations. Here, dotted line is also there that represents doping concentration. Here both curves represent doping concentration. It is about 10 power 21, it is about 10 power 24 atoms per meter cube. Like that, with increase in temperature or with increase in doping concentration, Fermi level decreases, and at high temperature or at high doping concentration, Fermi level gets equal to intrinsic Fermi level. This is the variation of Fermi level in N-type semiconductor. I hope it's clear. Now when it comes to the P-type semiconductor, same way, this is valency band and conduction band, and this is forbidden band gap, and this is intrinsic Fermi level. I hope it's clear. Now in case of N-type semiconductor, P-type semiconductor, there exists Fermi level in between valency band and acceptor level, because in acceptor energy level there exists holes, not electrons. That's why the Fermi level position is exactly middle between valency band and acceptor energy level at T equal to 0 Kelvin temperature. At T equal to 0 Kelvin temperature, Fermi level is exactly middle between valency band and acceptor energy level. Now, similar way, when we increase temperature and doping concentration, Fermi level increases. Here Fermi level increases with increase in temperature and doping concentration. Fermi level increases at certain high temperature and at certain high doping concentration. Fermi level gets equal to intrinsic Fermi level. This is in case of P-type semiconductors. I hope it's clear now. This variation of Fermi level can be measured by using these expressions. Anyhow, this can be derived by using carrier concentration expression. Here I given directly that expression, EF equal to ED plus EC by 2 plus KT by 2 log ND by 2 into 2 pi ME star KT by H square whole power 3 by 2. Here ED is nothing but donor level energy, EC is nothing but lower energy level of conduction band, K Boltzmann constant, T temperature, ND is nothing but doping concentration, ND doping concentration, ME star is nothing but effective mass of electron. By using this expression, we can calculate Fermi energy at any temperature in case of N-type semiconductor. Similar way, by using carrier concentration expression, we can derive the Fermi level expression. In case of P-type semiconductor, EF equal to EV plus EA by 2 minus KT by 2 log NA by 2 into 2 pi MH star KT by H square whole power 3 by 2. Same way, here EV is nothing but higher energy level of valency band, EA is nothing but acceptor energy level energy, K Boltzmann constant, E temperature, NA is nothing but impurity concentration, acceptor impurity concentration. By using this expression, we can calculate Fermi level energy at any temperature. This is about today's lecture. Now let us summarize these all concepts. We discussed about semiconductors. Anyhow, semiconductors plays a major role in electrical devices because of negative temperature coefficient, or with increasing temperature or doping concentration whose conductivity increases. Whereas in case of conductors or metals, with increase in temperature or doping concentration, conductivity decreases. That is important property of semiconductors. Again, charge carriers or electrons and holes. In case of semiconductors, both electrons and holes are involved in electrical conduction. Whereas in case of metals or conductors, we are going to discuss about electrons are only the charge carriers. Next thing, conductivity increases with increase in temperature and doping concentration. Already we studied with that graph. And variation of Fermi level in intrinsic and extrinsic semiconductors. Anyhow, in case of intrinsic semiconductor, Fermi level is exactly middle between valency band and conduction band. In case of extrinsic semiconductors, it is going to varies. In N-type semiconductor, with increase in temperature, Fermi level decreases. In P-type semiconductor, with increase in temperature or doping concentration, Fermi level increases. This is today's class. I hope it's clear. Thank you to one and all.